Hello, my name is Roy Simpson. I'm a professor of mathematics at Cosumnes River College in Sacramento, California. In this lecture, I'm going to talk about the laws of exponents. Specifically, I'm going to use this as a review for intermediate algebra. You should have, if you're in intermediate algebra, already seen the laws of exponents in your elementary algebra course. So this will be a very cursory review. I will still go ahead and prove some of the laws, but I definitely will not spend a lot of time doing examples. But hopefully this will get you back up to speed on the laws of exponents and clarify any misgivings that you may have. Now in this lecture specifically, I'm just covering these 5 laws. B to the m times b to the n is equal to b to the m plus n. Little note here that b is called the base of the exponent. And these m's and n's are called the exponents, or the powers. Okay. The second law says that b to the m over b to the m is b to the m minus n, and so on and so forth. You can read through all of these. Please note on the last law down here, it assumes that b is not equal to 0. If it were equal to 0, you'd be dividing by 0. Let's go ahead and at least prove the first one. We might prove all of them if I feel like it. The first one being that b to the m times b to the n is equal to b to the m plus n. So here we go with the proof. Well, b to the m power times b to the n power. Let's take the first chunk of it here. B to the m is essentially b times b times b, and so on and so forth. It's a shorthand for that multiplication where there's m of these things. So let's write m times. That's the exponential power is just a shorthand for repeated multiplication. Also, the b to the nth power can be written as b times b times b, and so on and so forth. And that's a shorthand for those b's multiplying each other n times. Well, if you think about that all together, how many times is b being multiplied? Well, you have m times there plus another n times there, so you have m plus n times. So if I say I'm going to multiply b against itself m plus n times, that's the same thing as saying b to the m plus n power. Now let's take a look at the third property. The third property is very interesting to me. B to the m to the n is equal to b to the mn. So in other words, exponents raised to exponents end up multiplying. And this one often trips students up. Actually, both these students get confused on both of these. So the first one should now be obvious. If I have some variable to the 10th power times the same variable to the 19th power, I have 10 of them here, 19 of them there. Altogether, I'd have 29. But what happens when it's powers to powers? Well, this theorem's saying that they multiply. Here's the proof. B to the m raised to the n. Well, let's see. Inside that parenthesis, you have b multiplying by itself. M times. But this nth power means that we have n groups of that. In other words, we have this b times b dot 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 times b, and that's m times. Oh, that's my dog. And then we multiply it again. B times dot 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 times b. And again, there happens to be m of those in there. And we keep doing this. Dot dot dot. The question is, how many groups of these groups do we have? Well, this power says we have n of these. So n times. So I have n groups of m. Well, another way to say that is if I have 10 groups of 8s, Well, that's 10 times 8. If I have n groups of m's, that's m times n. So that's the same thing as b to the m times n. That's how that proof goes. All these proofs are very straightforward. Maybe I'm a little bored to continue on with this, so let's just go straight into examples. Okay, so I have an example of simplify each of the following. We have 3 sub-examples. Part A is 3 to the 5th times 3 to the 18th. And that exponential notation really makes it easy for us to do the work here, because if you were to grab a calculator, 3 to the 5th is a large number, but 3 to the 18th is a huge number. It's much better since they have the same base, and they must have the same base. So these bases here must match up in order to use the laws of exponents. These have the same base, so this will be 3 to the 5 plus 18. I have 5 of them in the first one, 18 of them in the second one. So it's 3 to the 23rd power. I would not compute this. Okay, that's a great way to write 3 to the 23rd, because if you grab a calculator, it's just too long of a number, and some calculators probably wouldn't be able to do it. Example B, we have x to the 10th times x to the 7th. Again, notice that all the bases here are exactly the same. That allows us to link these up here. What's nice about this example is that there's a little missing and hidden number 1 here. If there's not an exponent that was distinctly given to you, you can assume that it's to the first power. So if they say x, they mean x to the first. You have one of them. So let's see, I have 10 x's there, another one there, another 7 there. Altogether, I should have 10 plus 1 plus 7, or 18 of them. There we go. Often I won't even bother adding them up. I'll just add them up in my head, but I thought I'd take my time there. Example C, we have a negative 3z squared times the quantity xz cubed times 1 minus x cubed. Now, this is a distribution of polynomials, so let's deal with the front end of this business first. Let's clean that up. Now, because this is a review for intermediate algebra, this should be still okay for you. I'm not really blowing your mind with this stuff. Remember, multiplication can occur in any order. So I could say it's negative 3 times x times z squared times z to the 3rd. Multiplication is commutative, so I can move those objects around. Now in the back end, this is a binomial, so I'm going to wait on that. And because these two factors have the same base, I can add their exponents. That's going to be negative 3x times z to the 2 plus 3, or 5, right? We have 2 z's there and 3 z's there, so altogether we have 5 of them, times 1 minus x cubed. And then finally, I'm going to distribute this picture, and that's the way I always think of it. I think, well, we have some picture that's hanging out front here. Let me go ahead and highlight it. We have this picture right here. It's hanging out in front of this binomial. So what I'm going to do is take that picture and distribute it into the binomial. Each object in that binomial gets this picture. So the first object, which is just a 1, gets this negative 3xz to the 5th. I'll just say times 1. And then minus the second object also gets that. And notice how I'm using parentheses here. You should, when I distribute across parentheses, I sort of leave the operation that they had. They had a minus sign there. I rewrite that. And then when I distribute it in, I just distribute it. I basically box this up with a set of parentheses around it and throw it against each of them. So I could have put parentheses here too. And it makes it a little bit cleaner, because now I can see negative times negative here becomes a positive. So I'll have this negative 3x z to the 5th. By the way, times 1 is just that. Negative times negative is positive. And 3x, and I'll move this x cubed forward as well. X cubed z to the 5th. And again, those x's have the same base. So I have x to the first times x cubed. So that will be a positive 3x to the fourth z to the fifth. Now, I'd like to make you, or maybe draw your attention to something that is very important. Now, this lecture is not about combining like terms or anything like that, but some students still have issues with combining like terms. So let me just remind you of when you can combine things and when you cannot. Right now we have a negative 3x, and I'm just writing it a little bit larger so I can do something. Negative 3x z to the fifth. And then to that we're going to be adding 3x to the fourth z to the fifth. These can go, you can add these up if and only if the stuff after the coefficient, so this junk that I'm highlighting, basically everything after the 3, everything after the 3 and the negative 3 here, if those pictures are exactly the same, you can add them up. The way I kind of teach this in class, I don't know why, it's very elementary the way I do this. I just thought of it one day when I was teaching. I thought, oh, it's kind of like, I've always thought of it this way, that you have a trailer truck, and this is kind of the truck part of it, and this is the trailer. I know this is very stupid, okay? I'm only saying it because for some reason people understand it this way. This is the truck, and everything on the back end there is a trailer. The only way you can add these up is if the trailers are the same. If the trailers are exactly the same, and you had, let's say, 5 times x z to the fifth here and 3 times x z to the fifth there, you can say, well, I have 5 of these trailers plus another 3 of these trailers, so I altogether have 8 of those very same trailers. But in this case, these two trailers are not exactly the same, so these are unlike terms. So I just want to make sure that that you realize that you cannot add these up because they're not exactly the same. They differ by a few powers for x. So let's try some other examples here. Let's simplify some of these. Part A is 7 to the 82nd power, which is, again, a very huge number, over 7 to the 80th power, which is also a very huge number. I would not want to grab a calculator and figure out what both these numbers are. Just wouldn't work out nicely. But we have a theorem that says that if you have the same base, which these two have the same bases, then it would be the top power minus the bottom power. And often in a class, I say, which has the higher power? That's the guy who wins. So the top has a power of 82, the bottom has a power of 80. Who wins and by how much? The top wins by 2. That's a great way to think about it. The top wins by 2. If you follow the way that most authors teach it, which is absolutely fine, it's correct and mathematically, they teach that it's 7 to the 82nd minus 80. And of course, 82 minus 80 is 2, which is mathematically correct in both cases. The reason why I say who wins and by how much is because in the long run, it'll help us out. It'll speed us up, it'll help us out, and get you still the same understanding. You're canceling. It's like you have 7 times 7 times 7 times 7. You have 80 groups of 7s down here and 82 on top. So a bunch of them cancel back and forth except for the last 2 on top. By the way, 7 squared, a good instructor would never accept that as an answer. 7 squared is 49. All right. Part B, we have t to the 17th over t to the 5th. Now, over here, I'm just going to do it the way the authors do it. It's t to the 17th minus 5, which is t to the 12th. But that's not actually how I do it. I just say, listen, who wins and by how much? Who's bigger and by how much? The top is bigger. By how much? 12. 17 minus 5. And here's the real reason why I say it, or why I do that. Example C, you have 3k to the 13th, m to the 3rd, divided by 6k to the 7th m to the 10th. You take care of things one at a time here. The 3 can go in that 6 very nicely. 3 goes in the 6 twice. So in other words, you can divide top and bottom by 3. And you're left with 2 downstairs and a 1 upstairs. Okay. And that should be old arithmetic stuff. With the k's, so these are the same bases on these k's. This k and this one. So who wins and by how much? The top wins by 6. The m's, maybe I'll use a different highlighter. The m's have the same base. It's m to the 3rd on top. It's m to the 10th on bottom. Who wins and by how much? Well, the bottom wins. By how much? 7. Right? There's 7 more of them on bottom. So that's why I say it, because it's just faster that way. Theorems really kind of slow us up sometimes. Oops, I was about to write the wrong thing. I can't abide by having that incorrectly written. So k to the 6 over 2m to the 7th. Our next example set is again a simplification process. Example A has 2 squared raised to the 5th. This basically means we have 2 groups of 2's in here and we have 5 groups of those. So altogether we should have 10 groups of 2's. 2 to the 10th. Now some people might say, well, that's 4 to the 5th, and they figure out what 4 to the 5th is, but which would give you the same answer actually, 1024. But I personally like to do it where powers to powers will just multiply. It's a little bit easier for me to do that way. Example B, we have z to the 8th raised to the 4th. Again, this is 8 groups of z's in here. Basically 8 z's. And you have 4 groups of those. So that would be z to the 8 times 4, or z to the 32nd. These last 3 examples I stuck in here. I normally don't lecture on this, but I think this is such an important topic. -5 squared. Now, a little note that I want you to take away from this online lecture. Powers, or exponents, whichever you want to refer to them as, they only affect what they are directly touching. So if I look at this exponent right here, it is only directly touching that 5. So that exponent is saying, hey, I have, let me write this negative out front, I have 5 times 5. 5 multiplied by itself twice. I better not write a parentheses, that might get confusing. So it's a 5 times 5, or in other words, a -25. There's a significant difference between C and D. D, you have this -5 squared. But this exponent here is directly touching this parenthesis. A parenthesis is like a suitcase. It's a grouping term. So in that suitcase, basically the square is affecting everything in that suitcase. It's saying whatever's in this suitcase, multiply it by itself a couple times, please. And -5 times a -5 is a +25. Note the difference. The exponent right here is only touching the 5. The exponent right here is touching the suitcase, or the briefcase, or whatever you want to call it. And that contains a -5. So this is going to be a -5 times a -5. And then the last one is just, some people tend to use multiplication when they shouldn't. -5 times 2 is actually a -10. But note, -5 to the 2nd power is not equal to a -10. Okay, so this is not a multiplication of 5 against a -5 against 2. It is -5 multiplied by itself twice. Okay. The next example set here, we're almost done, is simplifying these expressions. We have the quantity -3x to the 4th, z to the 8th raised to the 4th power. Now, when I work on the inside of parentheses here, I want to, I want to follow the order of operations, which essentially states that we should clean up the inside of parentheses. Well, I'm inside here, and there's really nothing to do on the inside of the parentheses. So what I will do instead is I will apply this fourth power to every factor in the parentheses. In other words, I will have a negative 3 to the fourth power, I'll have x to the fourth power, and z to the eighth to the fourth power. Now, a lot of students love to say they distribute the 4. That's actually not what's happening. Distribution is for multiplication only. Distribution makes no sense when you're talking powers. And if your teacher says it, they're wrong. Distribution really is axiomatically described to be in a multiplication. Whereas applying a power, we have a theorem that basically says if you have a couple things multiplying and they're raised to the same power, or basically you have a chunk, a briefcase raised to the nth power, then every object in the briefcase or every factor in the briefcase gets raised to the nth power. I do want to place a warning here before I continue on with this. I'll place it down at the bottom. Warning. We never have seen anything like this. We haven't seen this business. This is not true. Not true, not true, not true. I will often say it in my courses that I teach that addition and subtraction are the worst operations. They're the easiest for us to perform. And so because they're so easy and they're the first ones we learn, people often get lulled into this thought process that they can do anything with addition and subtraction. But it turns out they're the worst operations. What you want to be true with them is rarely true. In other words, we would love it if a plus b quantity to the nth power would be a to the nth power plus b to the nth power, but it's just not true. Just like the square root of a plus b, that's also not equal to the square root of a plus the square root of b. I mean, there's instances, if you've ever taken a trig class, sine of a plus b is not equal to sine of a times sine of, or plus sine of b. I mean, nothing, almost, I don't want to say nothing, but it's a rare instance where what you want to be true with addition and subtraction are actually true operations. So, or is actually true. It just rarely works out. All right, back to our example. So we have negative 3 to the fourth power. That's negative 3 times negative 3, which is a positive 9, times another positive 9, basically. So that's 81. X to the fourth is x to the 16th. And z to the 8th to the 4th, we've actually done that one. That's z to the 32nd. Example B here. By the way, I can do nothing else there, right? That's as clean as it gets. Example B, we have a negative x times the quantity x cubed to the 4th times the quantity negative x cubed raised to the 2nd power. And what I would do here is I work on the inside of parentheses first, look in there to see if either of those clean up, which they don't. And then I would apply these exponents to the parentheses. So leave that negative x out there. X cubed to the 4th is x to the 12th. And negative x cubed to the 2nd, well, negative number being squared becomes positive. And x cubed to the 2nd is x to the 6th. And now we have a negative times all these positive numbers, so that's negative. That's x to the 1st. So what do we have? 18, 19, x to the 19th. There we have it. Now I'm feeling a little bit like I could challenge you guys for no other reason than I just want to. So sometimes you get stuff that looks like this. 3x squared y to the 6th z to the 18th divided by 21x y to the 4th z to the, let's say z to the 20th. And this is all being raised to the 2nd power, let's say. Follow the order of operations. leave that parentheses huge and leave the 2 outside. The order of operations says work on the inside, silly. So I'll put my fraction bar in here and I'll start cleaning up. 3 goes in 21 7 times, so that. The x's, well, they have the same base, x squared and x. So who wins and by how much? The top wins, right? By 1. The y's have the same base. We have y to the 6 on top, y to the 4th on bottom. Who wins and by how much? The top is the winner. It's a bigger number by 2. Z to the 18th on top, z to the 20th on bottom. Compare them. Who wins by how much? Well, the bottom wins. It's a bigger number on the exponent on the bottom, and it wins by 2. So let me clean that up so we can see what we have. We have x y squared over 7z squared, and this whole thing is being squared. Now, because there's no addition here or subtraction, like I warned you a moment ago, if there was some type of addition or subtraction here, we'd pretty much, I pretty much wouldn't go any further. But because there's no addition or subtraction, it's just multiplication, I am going to apply the squaring process to each of these objects. So I'll have an x squared in the top, I'll have a y squared being squared up top, I'll have a 7 squared on bottom, and I'll have a z squared on the bottom as well. And cleaning this up, finally you get x squared y to the 4th over 49 z to the 4th. There's nothing else that I will cancel here. A fraction is simplified when there's no common terms between numerator and denominator, right? And so this is, or common factors, I should say. So there are no common factors between numerator and denominator. We are completely done. Now, as an additional example, if you have seen functions, if your instructor has covered functions already and now you're getting into a review of exponents or whatever, then go ahead and continue watching. If you haven't seen functions, you could just stop watching this right now. But if you have seen functions, we're going to let g of x be a function described by 2 times x to the 5th. And I just want to take a look at a few things. Let's look at g of 2a, and then we'll look at 2 times g of a, and then we'll look at g of a squared. Then we'll look at the quantity of g of a being squared, and maybe I'll even look at g of ab and g of a plus b. So we're evaluating this function 6 different ways here. Now remember, with a function says whatever's on the inside, that's my input, I'm going to plug that in wherever I see an x. So I have 2 times junk to the 5th power. That junk is actually that 2a. And can you see why I've done this example in this section? So we have 2 times 2a to the 5th. Well, remember, this exponent here, since there's a product in here, this exponent applies to each of the factors. It doesn't distribute it, it applies to each of the factors. So you'll have times 2 to the 5th and times a to the 5th. 2 to the 5th, by the way, is 32. And of course that would be 64, a to the 5th. The second example is slightly different. It's twice g of a. Remember, wherever I see an x in the original function, I'm going to replace it with whatever this is. So my function g of a is going to be 2 times a to the 5th. Instead of 2 times x to the 5th, it's 2 times a to the 5th. And of course, 2 times 2 here will be 4, and then a to the 5th. Now let's look at g of a squared. Let's see, so it's 2 times junk to the 5th power, and that junk is a squared. A squared to the 5th power is a to the 10th. And g of a squared. So we have something being squared. That something is the function g, which is 2 times junk to the fifth, where junk is a. This is, again, 2a to the fifth to the second power. That second power will affect both the coefficient and that a to the fifth. So I'll have 2 squared times a to the fifth being squared. 2 squared is 4. A to the fifth squared is a to the 10th. G of AB. Remember, our function is 2 times junk to the fifth. What we're plugging in for junk is AB. So that 5, again, because it's a product, that 5 will apply to both of the factors. So it'll be 2a to the fifth, b to the fifth. Notice that the exponent doesn't apply to the 2 because the exponent's not touching the 2. It's only touching what's in this briefcase. Finally, we have g of a plus b. Remember, g is the function 2 times junk to the fifth. And we're going to plug in to that blankness there, a plus b. Now, in this case, remember my warning. It is not a to the fifth plus b to the fifth. It is just what we have written here. This is as good as it gets. Well, technically, we could do something. For those who have taken elementary algebra or have already gone through polynomials in intermediate algebra, you know that we could expand out this binomial. But that's a horrible expansion unless you use something like Pascal's triangle. So this is done. Okay, because it's not equal. I'm just letting you know again. I'll keep repeating this. It's not equal to a to the fifth plus b to the fifth. Okay, definitely not.